Hello everyone, it's my pleasure to introduce Joe Hellerstein, who's a professor at UC Berkeley. So Joe is a very well-known personality in database research, and he's a winner of 2 Test of Time awards, Sigmod Test of Time awards, and a whole bunch of other awards. In fact, he won the most recent Sigmod Test of Time award on the work on online aggregation. So, but unfortunately his talk has nothing to do with things he won his awards for. So without much delay, let me hand over to him. But one thing I do want to mention is we're going to have a 1-hour slot, probably 50-55 minutes of talk and questions. So remote locations, that is UNC and NC State, get first priority in asking questions. So Duke folks should hold on to your questions until the questions from UNC and NC State are done. And that's pretty much it. And when you ask questions, please use your mic so that the questions, they can hear the questions as well. That's it.
Thank you all for the invitation. It's good to be here. This is a really dead room, so folks on the microphone, if I start shouting, it's because I can barely hear myself in here. Do you guys hear me okay? Yeah? There's very little echo in here, so I'll try to jump up and down and shout. Hey, you're late.
No, we're not.
Come on in. All right, so let's see. Today I'm going to talk about about declarative networking. And the title of the talk is not a question, all right? The title of the talk is a declarative statement, so it ends in a period. It is the first of many declarative statements we will make today. So this is an assertion that the next thing is actually what, and what is the next thing. So I'll try to explain what that means in a minute. I do systems work for the most part, and like most good systems work, this is collaborative with lots of people. A bunch of people at Berkeley, both students and faculty. I'll single out 2 students in particular, David Chu and Tyson Condi, who worked and are working quite a lot on this stuff, and my faculty collaborators Scott Schenker and Jan Stoika. Some of the other students that have been involved as well are up there. Former student Buntao Lu, who's now at UPenn, who you met last year here at Duke. And those of you who saw his talk will see some familiar material again this year in perhaps a slightly bigger context. And then a bunch of collaborators from Intel Research and former Intel Research people, from Carnegie Mellon more recently, from Stanford. It's a big bunch of people, many of whom are quite wonderful. So I couldn't have done this by myself by any means. All right, so this talk is seated in a time of great change. And you'll forgive me when I get invited to do distinguished lectures, I go a little over the top with the slides. So at least at the beginning, you have to indulge me a little. So there's change happening out there that's motivating this work. And so I did a little web search for Google image search for the word flux. So there's a lot of flux going on. And I found, well, we'll get back to that. Sorry. So there's 2 sources of flux going on. The images come later. The first is in the networking context. All right, the internet is changing. It's changing in many ways. Some people think it's evolving. Some people think it's ripe for revolution. But everybody seems to agree that the nature of the internet as we've come to know it is about to undergo quite a bit of change. This is a cover of The Economist that's an article more or less about sensor networks, about the idea that what happens when everything is networked. Your car, your seeds, your trees, your cows are all on the internet. What does that mean for information, and what does it mean for the network? All right, so some people believe that this will be an evolutionary change. Some people believe we have to redesign the internet from scratch. Okay, and some of the examples of this in the field, we've got the Genie project from NSF, which is roughly a testbed for revolution. The wireless sensor network space, they're really reinventing network protocols in a free way, kind of from scratch. On the flip side, in terms of evolution, there's a lot of people working on things like overlay networks that can run on top of the existing internet but introduce new functionalities incrementally over time. And then things that are going on in data centers at places like Google and Yahoo, a larger and larger fraction of the internet is back there. Okay, and they get to do their own changes. They have to be consistent with our view of the internet, but they get to do interesting things behind their walls. And as more of our computing goes into these data centers, more of the network is there and evolving without actually much knowledge on our part as to what's happening. So there's a lot of change happening. It's a time of great ferment on the internet. All right. The second phenomenon that I'm very excited about as a guy who has a background in databases is what I like to call the industrial revolution of data. All right, and this relates also to places like Google. And the idea here is that we've had an amazing decade of text processing. all right, on the internet with the start of the World Wide Web, roughly the early 90s till now. And when you think about it, text processing is really quite quaint. There's all these nice people who are sitting at their keyboards typing in information, character by character. And we're gathering all that information together and we're getting knowledge out of it. And that's been quite amazing for the last decade. But really, when you think about it over time, it's a very old-fashioned mode of production to expect that individuals will, by hand, craft content, and that will be the raft of information that we'll be dealing with in the world. I predict, and it's really happening, that what's the largest form of production of data will be automatic production of data. Data will be stamped out in data factories, all right? It will be pumped into the environment, and most of the data in the world will be actually manufactured, not created by, nice British ladies in the basement with knitting needles or keyboards, okay? So data is going to come from things like sensors, RFID streams, software systems generating logs, all right? It can't be the case that in 10 years most of the world's data will be hand-typed. There just aren't enough monkeys and aren't enough keyboards to keep up with the data that's going to be auto-generated. Okay, so we have an environment where the network is changing and the sources of data are changing. And we're going to see both of these things really come to the fore in the next decade. And the question is, in this time of flux, and now I get to move to my Google image search for flux. This is some artist's piece called Flux. In this time of flux, how do we take advantage? So whenever there's churn in an environment, it's opportunity, right? So the question is, how do we take all this free energy and harness it and get it working for us? And my answer to that question is what? So my feeling is, in this time of flux, what can harness and accelerate the energy and innovation in this space? Something about whatness is going to be what allows us to take this energy and bottle it up and use it. So what am I talking about? I'm talking about what? So what is the future? Declarative networking. So when I talk about what, I'm talking about declarative languages, languages in which you say what you want rather than how to get it. All right, and that's the classic definition of a declarative language. Networks these days are implemented in a how form. You say how the network should work. You say, I pass you a message and then you send me a certain message back. There are protocols, okay? But really it's quite natural to think of networks in terms of specification in a kind of what sort of way. So for instance, the topology of a network. It might be nice to say, I would like to have a network. I want to make sure none of the paths are longer than such, and I want to make sure that the in degree at any given node is not more than this, and I don't want the load at any node to be that. And please lay out a network for me. I don't care about the details. All right, that's topology by specification. Similarly, routing constraints. I might like to say, look, I want to get a packet from Duke to Berkeley, and I don't want it to go through MIT. Okay, route it however you want. I just have some constraints on this packet. Okay, so again, routing might just be by constraint. What do I care what particular path it takes, as long as I'm happy with a class of paths? Addressing by content is another one that's been very popular in the distributed systems community. So I want to send a message, and I want it to get to my friend Bob. Okay, so I'm going to put Bob's name on the message, route to Bob. I'm not going to put his IP address because I don't know what machine he's on right now, and frankly, I don't care. I just want it to go to Bob. Okay, and as Bob moves around in the world, or as Bob's computer moves around, his computer presence moves around in the network, the messages should just find him. All right, so these are all things where it's fairly natural to think about specifying them in a what kind of way rather than a how kind of way. And when you think at this level of abstraction, you suddenly can do a lot of things relatively easily. And I'm going to try to convince you of that today. So once you can say things in terms of what, you can do lots of more interesting things like who and where and why and when. So with our language and our system, we've seen people working on things like authentication, geolocation, consensus, forensics, all kinds of questions that would seem like they'd be very hard to implement when you start with network packets and protocols, but turn into fairly compact programs when you start thinking about things declaratively. And then this is the key that comes from the revolution of data stuff, okay, which is that what we're going to do is we're going to try to get on the network a marriage of the data and also reasoning and control. So we're going to build into the system by having a declarative interface and being able to ask for things by specification. Natively, we'll be able to do things like search, find me things such that X, and query, and then more interestingly in our recent work doing statistical inference and possibly movement of data and possibly movement of devices. Okay, so that's at a very high level. How did I get into this? I'm a database guy by training. So let me give you a little background on how I got into this what business. So for many years I was working on systems, both peer-to-peer systems and sensor network systems that were trying to query data that was distributed in a network. So we started out by saying, look, there's all this data on the web. Let's build a query engine that grabs it from all the different places, puts it together, and mashes it up. We didn't call it that back then, but that's what we did. And after some time, we said it'd be more interesting if the query processing wasn't all in one place. It was collaborative. So we were actually running the queries in the network. So in a sensor net, many nodes would participate. Or in a peer-to-peer system, many nodes would participate running the query in the network. And after doing this for a while, we had this weird epiphany that these networks were actually doing things that we could say in queries. So rather than querying the network, we were actually implementing the network using queries. And that's what the background for today's talk is. And then finally, where we're moving to, sort of in the work we're starting now, is integrating the queries and the networking along with the management of uncertainty and statistics in the data. And it's this synthesis where this stuff gets, I think, really exciting. And this is the next generation of this project. So what I'm going to do today, then, is I've given you a little background. I'll give you a little motivation on why this is worth doing. So that's why what. All right, then we'll go through say what, which is a little bit of a language primer on the language we use for this. Some of how we implement this, that's the what how part. And then some applications, what for, and research directions, what is next. And then finally, hopefully convince you this is relevant, so that's what's it to you. So that's the outline for today's talk. Okay, why what? Well, the traditional motivation for declarative languages is that they're at a high level, so they make it easier to program. And many of the metrics in our papers say things like, our programs are small. Our programs are easy to understand. And I'll show you examples of this throughout the talk. All right? And when I say that, I mean it better be radically smaller. All right? They have to be qualitatively smaller than traditional programming models. And I'll demonstrate that to you. Once you have that, then it becomes easy to do things like rapid prototyping. All right? Maybe it's not the most tuned implementation, but if you can bang it out in a dozen lines of code, you can try it out and then customize it very easily because it's easy to understand, it's easy to change. All right. I will argue to you today that distributed languages are actually well suited to many, declarative languages are well suited to many distributed tasks. So surprisingly, these languages that came up for deductive databases are actually very good at talking about data distribution and protocols. Okay? And then I'm also going to make the argument, and I'll show you an example, that by specifying things at a high level, you actually get to see conceptually a bigger picture. And you somehow take the ideas that have been embedded in the networking research and you can up-level them and see their synergies a bit. Okay, so I'll show you at least one example of that. Another motivation for using declarative languages is that you can optimize them automatically because the thing hasn't said how to do things. The system can choose how to do things, and it can make different choices at different times or at different points in the network. Okay, so you get automatic optimization. And I won't talk about that a bit actually today, I won't have time, but we do have work in that area on state management and network rendezvous and how you can optimize that. One thing we haven't gotten going on that's very important is when you have a high-level declarative language, you can prove things about it. All right, so there's various things you can do to prove the safety of protocols, both at static checking time and by inserting automatically dynamic checks into people's programs. So it gives you the ability to deploy distributed code in a network and have some proofs about its behavior and constraints on its behavior. And that's a powerful aspect of declarative languages that we've yet to exploit in my group. Okay, so this has all been very high level. What I'm going to do now is jump to the endpoint. What have we built so far? And then fill in the middle of what's this all about. Okay, so just quick list of things we've done. So in this context, we've implemented textbook routing protocols, both internet protocols and wireless protocols. And these were things that were like a handful of lines of code. Okay, and they were running in networks. We then looked to be more ambitious and build complex overlay networks. So we implemented distributed hash tables in our system called P2. So you know you have a system when it has a dorky logo. So that's the P2 logo. And that was work at SOSP. Following on to that, people at Intel did things with distributed debugging where they were able, because the program was specified at a high level, they were able to trace its behavior and attribute messages that were received to the reasons and the sources for those messages being generated. And it gave a very high-level notion of debugging, including distributed watch points. You could say, if the network as a collective ever gets into a certain state, stop. It's very powerful. So it's sort of GDB on a distributed computation. And they were able to implement Chandy-Lamport snapshots to do this in very small lines of code. Okay? Crazy graduate students at Harvard took our system without our knowing it and implemented the Paxos consensus protocol in 44 lines, which was a surprise to us because we really weren't intending for the system to be used for these sort of distributed algorithms. So that was something that happened early on. So those are some of the early things that happened. In the last year or two, we've had a paper at Census this year on our SensorNet implementation of this language. It's a system called DSN, Declarative Sensor Networks. This is probably the fullest realization of the idea in the networking context, because we took almost all the layers of the networking stack and implemented them in declarative logic. Everything from the lowest level of radio link estimation, routing, including geographic routing, application level things like data collection, code dissemination, object tracking, localization, up and down the stack, were all little programs in our language. Okay. And then more recently, other folks, all of the rest of these citations are groups that are not my group, have been following on our work, either using our systems or using our language to do a variety of things. So Boon-Tao Liu and Martina Badi and others have been working on secure networking protocols based in this context. Folks in Mike Delean's group at Texas have been using this with respect to data replication. So they have a wide family of data replication policies they can easily implement in declarative language. The Penn folks also doing mobile networks. And then the craziest piece of this being Seth Goldstein's group at CMU, which is building modular robotics out of our language. So they've got little atoms moving around based on programs expressed in our language. And I'll show you an example of that from their paper later. Here's some of the topics we're working on next, and then finally we'll get grounded and we'll talk about how this all works. I'll talk about two of these three today. One is meta-compilation, so implementing our compiler in our language, which we've done in the last year or two, which is very cool. The second is distributed inference. This is collaborative with CMU, implementing machine learning inference algorithms to run in a distributed context in a very small number of lines of code in our system. All right, including some fairly fancy algorithms. And then the other piece I won't get to talk about today is the automatic optimization piece. Okay, so that was some of the background, some things you can do with this context, all right, gives you a flavor. Now let's talk about what's going on. We'll start with the language specification, and then we'll move into the implementation. Okay, I just want to give you a picture of one of our systems, the first of our systems, P2, which is the internet context of this stuff. At 10,000 feet, the system kind of looks like this. There's two language interfaces to the system. One is a logic language called Overlog, which is at the top there. The other is a data flow language. If you're familiar with MapReduce, it might look a little bit like that. Okay? And what we do is you can write things in either of those, whichever you prefer. All of our users use Overlog. We haven't gotten any customers for the data flow. So what happens with the overlog is it goes through a parser. The parser generates some internal representation, which goes through a planning phase and spits out a data flow program. These data flow programs are disseminated through the network so that every node has the same program. So it's a single program, multiple data mode of parallelism. Okay? And then these data flow programs start pumping packets and data through the network based on some clock. Okay, so that's a big picture of the system. It's a data flow system compiled down from logic. So how many people in this room, at least, had to learn data log at some point in their lives? Only the database geeks. All right, so this is a particular form of torture that the three of us had to go through in graduate school. And it was particularly considered torture at the time because everyone had agreed it was irrelevant by the time we were in grad school, I think. Certainly by the time you guys were in grad school, although you were at Stanford where they were true believers. But when I was at Wisconsin in the early 90s, it was already felt like, well, this was theoreticians doing stuff for theoreticians' use. So I'm reviving this stuff, okay? Which is part of the fun, frankly. But I need to give you a little primer, and what I'm going to start with is the boring example that we all got in class, which is you have a graph. The graph is a family tree, all right? I looked for a family tree on Google Images, and I got the family tree of IBM mainframes, which I kind of liked. So that's my example of a family tree. All right, and the canonical program you learn, it's a recursive program, and recursion is key to this, is the following. You say, we have some relation, parent, which has pairs x and y. X and y are variables, and if you have I think of it as a row in that table, right? You have a pair x, y, that means x is the parent of y. And from that, we're going to define some derived tables, and we're going to call them ANK, which stands for ancestor, and I never could figure out how you were supposed to say that. And ancestor is defined in a sort of inductive way. The base case says that if x is a parent of y, so here's a picture of x and y and z. If x is a parent of y, then x is an ancestor of y. All right, that's the base case. And the induction case is this third bullet here, which says that if x is a parent of y and y is an ancestor of z from a previous step in the recursion, then x is a parent of z. I'm sorry, x is an ancestor of z, right? Okay, and then you could do things like ask queries, like find me all the ancestors of S, okay? Or you could ask to find everything if you wanted. You could say ancestor x comma y question mark. All right, so that's data log. It was all the examples were things like this, or find me people in the same generation on the family tree, all these sort of abstract, silly problems. And so all that went away when the web came, and everybody worked on other stuff, because the internet changes everything. So on the internet, this is completely, actually totally relevant, it turns out. So this is exactly the same query, all right, but the names have been changed to protect the innocent. So instead of ancestors and parents, we have links and paths. And this is a reachability program. It finds pairs of nodes that are reachable from each other on the internet. So we say, look, if x has a link to y, then x has a path to y. And if x has a link to y and y has a path to z, then x has a path to z. Okay, same program. And we can even say things like, find me all paths to S. Okay, now the problem with that is that's just a reachability protocol, and what we want are the actual paths, right? It's not good enough on the internet to know who can reach whom. We need to know how to get there. We need to send the packets. So let's expand this program slightly. So the stuff in colors is what I added, okay? And let's look at this first rule. I added to this link table a cost field, C. All right, so every link will have a cost. You can think of that as a latency. Okay, let's use that for our example now. But it could be capacity, it could be a bunch of things. But let's use latency as our cost metric. And our base case of the rule is going to say if you have a link from x to y of cost c, you have a path from x to y of cost c. All right, so the c's are costs, and we just derived a cost. Okay, it's the recursive. Oh, and then there's one more thing we added, which is this y business. All right, and the y is the next hop on the path to get to where you want to go. So if you have a link from x to y, there's a path from x to y, and the blue thing is the hop you should take to go along that path. All right, and in the base case, it's the same as the destination. Now, in the recursive rule, this is where things get slightly more interesting. Let's do costs. Okay, so we have cost of a link from x to y is c, cost of a path from y to z is d, and we'll use for latency anyway, that the cost of the path then from x to z is their sum. If we were doing capacity, it might be their min. Okay, and you can come up with other little rules to put in there. All right, and then the next top part is only a little bit subtler. Just be careful here that when you say there's a link from x to y and a path from y to z that transits through n, the next hop on the path from x to z is actually y. Okay, and then when you get from y, you would go to n and recurse down the chain like that. So that's our little program, and now we have paths. All right, and that's nice. It's still not really a very good protocol because this is all paths in the network, and nobody wants to know all the paths in the network. They only want to know the best paths in the network. So let's augment our program to do best paths in the network. Okay? So what we're going to do is we're going to take our previous program, which we just had, and we're going to add a rule. This rule says if there's a path from x to z of cost c, of all such paths, find the cost of the minimum. All right, so this finds the path from x to z of minimum cost, and it remembers the cost. All right, and then given the cost of the cheapest path, you stick it back together with the paths. That gives you that path whose cost c is the same as the minimum cost. All right, so the best path is the cost of minimum cost, the path of minimum cost. So this program now finds best paths. All right, and this starts to kind of look like a routing protocol. So now I can say for a particular source, find me all the best paths to all the destinations. All right, and this is roughly what internet routing protocols need to do. So that's pretty good. So we said that in 1, 2, 3, 4, 5, 6 lines, all right, 3 of which I learned in graduate school. That's pretty good. Okay, so what do we have so far? So far we have some kind of logic language for pathfinding on some virtual database of links in the sky. So maybe there's a world in which all routing actually happens at Google, right? And you go to Google and say, how do I get a route from here to there? And they maintain a database. But that's not how the world works right now, and frankly, it's kind of boring. So we would really like to know how this can lead to a distributed protocol. All right, so we had this intuition. We've gotten this far, but it's all a toy right now because it needs all the link information in one place. So next step, can this lead to protocols? And the answer is yes, and the fun part is how easy this is going to be, okay? So all we're going to do is we're going to take our tables, and we're going to split them up horizontally. We're going to slice them horizontally and put the pieces on different nodes. So logically, there's the tables in the sky. Physically, they're going to be horizontally partitioned across nodes. And the way we'll specify the horizontal partitioning is putting one of the fields in the table to be the address field. And we'll notate it with an @ sign. That's called the location specifier of the table. And your data placement will be based on the value in your location specifier attribute. And the cool thing about this is once we've done this, once we've said this simple little thing, we're going to get communication for free in our language. There will be no command in this language for send, and yet everything's going to make sense and work. So here's how this goes. Here's our program. I left out the best path part because it's totally local and kind of boring. We have a link table, all right? Source, destination, cost. And we put the @ sign on the first field, which is the source, which says that links will be stored at their source. So if we have a little network ABCD in a line like that, we take the link table, it's partitioned like this. The first attribute tells you where the tuple lives. Okay, and those vertical lines are that's cost 1 for all of these. Okay, so that's the first thing we do. That's how the data is laid out by declaration. So the base case of the program is very simple. We say if you have a linked tuple, you have the corresponding path tuple stored by its source, so it's at the same site. So that's, again, just trivial. We just copied up. Now here's the fun part, is the recursive part. All right, I would like to construct paths out of links and paths. Okay, the problem in this rule is that the path table is partitioned by source. The link table is partitioned by source, but I need to connect the destination of a link to the source of a path. So there are two different nodes, right? One is at X and one is at Y, and I want to combine by the Y's. Destination of the link, source of the path. So for example, I want to put together this link, A gets to B with cost 1, with this path, B gets to C with cost 1. And I want to form A gets to C with cost 2, right? And they're two different nodes, so I need to communicate. But we're not going to introduce the communication explicitly. Here's how this works. The system is automatically going to rewrite this program. It's going to say, gosh, you can't do that at a single site. So we'll rewrite the program for you. Oh, by the way, the results got to land back at the source, okay? Part of the deal. Okay, so we'll do this by rewriting the program. We call this the localization rewrite. We've taken that third rule and we've turned it into 2 rules. The first of them takes the link table and produces a derived table link underscore D, which is just partitioned by destination instead of by source. Okay, and remember this was automatically generated by our compiler. So link D looks like this. This guy sends, in essence, his link tuple to his neighbor. Okay, we do that for all the link tuples. So that's what happens because of that redistribution. Now that we've done that piece, which was just involves message sending, everybody sends to their neighbor, to their destination. Now we can do the second rule locally. So now we can combine destinations of links and sources of paths at a single node, right? So these two tuples that used to be in separate places are now in the same place. We can stick them together there, and the result by specification goes back to the source, right? All right. So a little rewriting, and our program is now doing all the communication. Nobody ever said send. Okay, we didn't have to think about this. All right. What's extra cool about this, if you like that sort of thing, is that this is a well-known networking protocol. This is the distance vector protocol. And when you learn about distance vector in class, which I actually never did because I never took a networking class, they say the way distance vector works is everybody sends advertisements to their neighbors about their link table, and the neighbors send back responses with paths. And then you send out more advertisements and collect more paths. And there's this sort of back and forth you go through. We got that here just by saying the data shall be in the following places. Right? That's what the program with the @ sign says. The data shall be at these nodes. All right, so there's no specification of a protocol. In this example, the pseudocode for distance vector is 7 lines long. It's not a complicated idea. All right, and our program is 6 lines long, also not a complicated idea. So you don't seem to get a lot of power out of this, but we'll see later on as we look at more complicated protocols that not having to talk about who sends what to whom when, rather just saying the data shall land there, all right, that we're going to get very compact protocols. And there's another really cool thing about this, which I guess I'm not going to get into, which is that you can throw a standard query optimization at this program of predicate reordering, particularly when you have selected sources and destinations that you care about. Then you get to use this well-known technique from deductive databases called magic sets reordering. And it changes this execution into a wireless protocol called dynamic source routing. You start with the same protocol, which says the routes shall land at the places. And a query optimization decides whether it looks like a wireless protocol or a wired protocol. And that optimization can be driven by measurement. Okay, so you can figure out that patches of your network behave unpredictably, and you should treat them as if they're wireless. Patches behave predictably, you should treat them as if they're wired. But you never said this is the wireless patch and this is the wired patch. All right, this is going to be very important as the network becomes more heterogeneous and there's cows and data centers and all sorts of other crazy things as part of the internet. Okay, so that's the language, and that hopefully gives you a flavor of what's going on. Okay, a little bit about implementation then, unless somebody would like to stop and ask a question about the language. Okay, let's plow ahead. So we saw this picture, okay? We're going to take our overlog language, we're going to translate it somehow into a data flow execution model. And then we're going to run that data flow on the network. So let me show you a little snippet of this. This is 3 rules. These are the lookup rules for the chord overlay data, the chord distributed hash table overlay network that we implemented. I don't want you to pay too much attention to them. You don't have to understand them. What I want you to see is that when we compile them, they generate this data flow plan. All right, and I just want to focus in on the distinctive pieces of this. This looks a little bit like a database query. It looks a little bit like a router, particularly a router in a configurable routing infrastructure like the one the Click system offers, which was a big inspiration to us. At the bottom of it, you've got tables as if it's a database. Okay, happens that we tend to keep these in main memory in our systems because routers usually keep their tables in main memory, but they could easily be in Berkeley DB or your favorite database backend. All right, or our local one is called Stasis. And then on the edges of this thing, there's networking gunk. Okay, there's things like queues and multiplexing and demultiplexing and congestion control, stuff like that. And for the moment, assume that this is just wrapped around the query in a static way. We do this right now fairly statically. We just stick these components around the edges of the data flow. And in the middle, there's the gray stuff, which is kind of database stuff mixed with networking stuff. So you'll see there's joins and aggregations and insertions and selections and projections. There's also some pushing and pulling and things like that going on, which is a little bit more routery. All right, so it's kind of the best of both worlds, or it's the kitchen soup of both worlds of router data flow elements and database data flow elements. All right, so we got it all in there. If you like to think this way, well, then by golly, you can write one of those data flows in a scripting language, as I said. Okay, so we have a language that let people say how instead of what. I would say 0 of our users like this language. We support it, and in fact, it's really nice to have because it separates our compiler from our runtime, and we want to retarget our compiler. It looks a lot like the Click language. It was inspired by a well-used language in networking. Nobody uses it, for what it's worth. Okay, so the next thing to look at is what for. So I want to show you some examples, non-trivial examples of what we've used the system for. And I'm actually going to show you entire programs, okay? I'm not going to step you through them line by line, but I'm going to show you entire programs that we've implemented using this infrastructure. So I changed the order on these based on feedback from another talk. But on the left, what you see is the pseudocode from a paper in Census by Phil Levis and David Culler and others on a code dissemination protocol for wireless sensor networks. So the challenge is you have a new version of code. You want to disseminate it to all of the nodes in a wireless sensor network and get them to reprogram. All right? And the problem with doing this is, first of all, it's a broadcast. You have to do the broadcast through gossip. But second of all, you have to make sure that they don't contend for the wireless medium. So they have to avoid collisions. All right, so they have to kind of back off so they don't collide sending their messages. All right, and he's got a very simple pseudocode for this, which is 7 lines long. All right, I'm not counting so well on the fly. 6 lines long of pseudocode. And on the right-hand side is our implementation. And our implementation is practically 1 line of pseudocode equals 1 rule in our program. Not entirely, but mostly. So except for the setup stuff at the top, and the cleanup stuff at the bottom, it's pretty much, there's a line of our program for each line of pseudocode. Our program's a little bit longer because we copied the pseudocode into the program. All right? Now, the program's not that pleasant to read. And if we picked a more pleasant to read syntax, it would be a bit longer. All right? But it wouldn't be as long as the C code, I assure you. It would still be within a factor of 10 or 100 from the C code that was generated. So to quantify that more carefully, first of all, I want to convince you that they run about the same. So we compile that down to NestC, to the language that's supported on the moats. And we get runtimes that are indistinguishable, okay, in terms of the time it takes for a new program to propagate out through the network for various configurations, roughly indistinguishable from the native implementation. Okay, so we took Phil Levis's code. We took what we compiled out of our protocol specification, and we got the same performance. Give you a sense of the program differences. So Phil's code was 560 lines. Ours was 13 rules, or 25 lines, to be very honest, the way we spaced it out. And then in terms of code size and data size, we're a factor of about 2 bigger. Okay? And our compiler can actually decide in DSN what to assign to the code segment and what to assign to the data segment, because some of the moats have more code segment space than others, Okay, but basically it's a factor 2 bigger, and what you're paying for is there's a base cost just to get our runtime installed. All right, so for little programs, that base cost counts for a lot of the program. right, but it's very similar in size. So I wanted to give you a nice pocket-sized example where we took pseudocode, almost line-for-line translation. We were able to generate a very compact program that runs with essentially the same performance. Now let's move to the internet domain. And this was the first big challenge we actually took up. Chronologically, this came much earlier. We wanted to take a big, complicated network protocol and implement it in declarative language. So we took the CHORD distributed hash table from MIT and Berkeley, which is an overlay network for content-based routing. It allows you to send messages to names instead of to IP addresses and rendezvous at the place that currently holds that name. We did a very faithful implementation with all of the bells and whistles from their research paper. Okay? And if you know that paper, these are some of the bells and whistles we added. And our program in the end was 48 rules long. Okay? And this is the program. Okay? I don't expect you to make sense of this. You can't even read it, all right? It's you know, right. All right, but you could print this out and you could take it to the coffee shop and you could figure it out. Okay, it's one piece of paper, all right? The MIT implementation is 10,000 lines of C++. You do not take 10,000 lines of C++ to the coffee shop and figure it out. Okay, so you can not like our syntax and you could think we're being terse and obfuscated and all that, but there's a qualitative size difference here. We're reasoning at a higher level. And for the programmer, it means that they can have a much better time expressing and understanding their programs. All right. And I think this is justified both by the size and also by the way that it seems to map so neatly to the way that people think about protocols. All right. Two sort of justifications for that I'll give off the cuff. One is that a lot of what happens in a network protocol is rendezvous. At some level, a sender and a receiver have to get some piece of data agreed upon and passed from one to the other. And it either happens by the sender sending it to the receiver, or the receiver going to the sender, or the sender and the receiver agreeing on some place in the middle to put the message and get it. All right? That is very much, particularly when you look at streams of such messages, very much like joins in a database. You've got a stream of messages here, you've got a table of messages there, you're matching all the things in this stream with all the things in this table. All right, so the rendezvous problem and the notion of matching these variables in these rules, what's called unification in logic programming or join in databases, are very similar. So there's this basic thing you do in distributed protocols that comes out of, matches nicely to a database operator. And then the second thing I'll say is that network protocols spend a lot of time talking about graphs, properties of graphs, doing transitive closures on graphs, and these deductive database languages were designed to express recursive properties on graph data. All right, so it's a very natural fit along sort of two dimensions. So it's not happenstance that these things ended up small. It's a good fit. Okay. So you might want to believe that P2's implementation of CHORD is good too. So we evaluated it. Sort of, does it work? Sort of metrics. Well, the lookup is logarithmic, which is what you'd expect. The median lookup latency is respectable enough for an application level thing. It's 1 and 1.5 seconds across a wide area. This is on Planet Lab around the world. All right, and we're using a very bandwidth efficient implementation. So our network traffic to maintain the network is ramped quite a bit down. All right, and stays pretty steady over time. So that just kind of shows you the basics. The interesting metric for a peer-to-peer protocol like CHORD is how it deals with nodes coming and going from the network with churn. And a lot of the logic in the system is about managing churn efficiently. So the MIT implementation of CHORD is really quite impressive. The metric for churn that they use in their paper is when at any given time, what percentage of the nodes in the network agree that the home of a name is foo? All right, call that consistency. So how often or what fraction of the nodes agree on the proper mapping of a name to a machine? All right, and they find if the average lifetime of their nodes, the half-life of their nodes is 47 minutes, so nodes stay on the network for about 47 minutes, 99.9% of the time, all right, their nodes agree on the destination of a key. And we didn't do quite as well, okay? We did pretty well. So that's the comparable number from our implementation. Still pretty good, okay? And I'll make two comments here. One, we're just a prototyping language, right? After you come up with your new crazy protocol and you write it in our system in 4 lines, you're welcome to re-implement it in C++, all right? But it's going to be much easier to prototype and manipulate and experiment with in our language. Then when you really got it baked, you implement it in C++. And it's very much the way things work in databases right now, right? Where you start by prototyping a high-level language like SQL, and then when you really get it right, you rewrite your application so it does all its data access in C++. Right? People don't do that, okay? So this is the slippery slope of the prototyping language, which is if it's good enough, you'll never implement things in the low-level language. The second argument, okay, is, we could get it to 99.9%. We just have better things to do, okay? We didn't tune this up much since we published the paper in 2005. So, question?
I was just going to ask if you had a sense of what accounts for the difference in
Yeah.
terms of behavior here.
Boone does, and I forget. So, yes, the answer to your question is yes. But don't ask me a follow-on question. I apologize.
So do they measure consistency by looking at samples at some regular time interval and saying how well did it do in each snapshot?
Yeah, I believe so. I believe what they do is they, at regular intervals, they ask for a particular key, maybe chosen at random from a seed, so they're asking for the same one, and they log it, and then later on they go back and look. I'm pretty sure that's how it works.
They're issuing queries which are actually propagating through the net. So it's not that the sites actually have to agree on who the home site is for each key, but the query resolution process has to.
Right, so
Get the
everybody
right
says,
answer.
where is Bob? They
Yeah.
write down what IP address they got an answer, and then they check that later on to see what percentage of the time everyone agreed. Or is it what percentage of people agreed at any time? I'm not exactly sure.
When you showed us the trickle performance data, you showed us how long it takes for the code to distribute through the network, and it was sort of indistinguishable whether you used your implementation or a previous implementation. But it's a little hard to tell from that where the time's being spent. It could be that it's all network latency,
Yeah.
and the codes, it's kind of, one could be 10 times slower and it wouldn't matter.
That's right. I have not claimed, nor would I claim, that we're CPU efficient right now in our implementation. And so the comment, I don't know if can people hear on the microphone the questions from the audience? Great. It says us. Okay. Given that, the time is absolutely in latency/bandwidth. I mean, it's in network communication. So in the case of Trickle, it's bandwidth constrained. Okay, getting these programs across.
Basically.
You basically have to do the right thing. That's right. So you got to get the protocol right, and that's the issue. And including in Trickle, there's a timing issue with it. And so in a coarse sense, we got the timing, the back off right, so we don't get contention. But I don't claim that we can do any kind of real-time timing well. We haven't bothered tuning for CPU performance because it hasn't mattered to us. I might come back to that, qualify that slightly in a few slides, actually. But for the most part, CPU, certainly in network protocols, has not been our bottleneck, and so we haven't worried about it. Now, if I was at Cisco trying to sell them this technology, we would have to have a longer talk, right? If you're actually building a high-speed router, there's efficiency challenges. Click, which is a data flow system that looks very much like the internals of P2, is supposed to do pretty well performance-wise. And so one would expect that with the right tuning, we could get there. They have a lot of nice C++ optimizations in the Click paper they use to do that. Okay. But data flow per se as an execution model seems to be almost competitive. Right? Maybe not at the very highest end, but getting pretty close.
Did you look at energy efficiency as a metric for your sensor nodes?
Good question. Did we look at energy efficiency for the sensor nodes? The answer is no, and that's a great one. We had a person who was thinking about using our stuff for energy policy specification, and it would have been natural to do it with him, and that sort of dribbled off on the wayside, and we haven't done the energy measurements. It's a great one.
So you
I
can't
would
just-
expect that's the flip side of the question, that we're doing not so well there. But I don't know. It depends very much on David Chu's compiler down to Nessie and what it's doing, and I'm just not sure.
So you can't just specify the energy behaviors in your specification.
No. This was to specify what the node should do under certain energy loads. Now I can't. I don't have an optimization process that will say that your program is not satisfiable with these energy constraints. That'd be cool. Maybe next year. Okay, I want to show you another example program from a paper not ours, from a system not ours. This is the MELD language that the guys at CMU have. So they have these things. Their vision is that we're going to have smart matter. It's going to be made up of little atoms, and the atoms are going to be autonomous little robots, and they'll do things like roll over each other, and they'll form shapes, kind of Terminator 2 style. Okay. Right now they got atoms. The pictures I've seen, they're like the size of a giant beach ball. Okay, they're atoms, but they kind of work. And so the idea was they need to program these things. They're going to have to communicate with each other as neighbors, so they were interested in networking and distributed control. And they want to be able to program them in a simple way. And they wrote this paper completely without my prodding that said, hey, let's program them using the language from P2. And they renamed the language MELD. They changed it around a bit to add some stuff. And this is their example from their paper of how you move your atoms to a target in 3 rules. So they have a rule for measuring the distance of each atom from the target. This is still single program, multiple data. Every atom runs this program. How far am I from a target is the destination, the distance, excuse me. And then there's a rule that says S is farther from the target than T if S is a neighbor of T and S's distance is further than T's distance. All right? And if you are further from the target than your neighbor, move around your neighbor. Okay? And move around is something that hits the control layer then of their things, and the things do the action. All right, so move around calls a function, essentially. Whenever there's a record in the move around table, it activates something. And so you can see, they start like that, and then this guy moves around because they're going rightwards, all right? Finishes moving, and then that guy moves around, and slowly the Terminator 2 goo finds you and covers you, and you are suffocated, or whatever they want to do. Okay, so that's a little example from the world of robotics, kind of nutty. So we're running out of time. I want to wrap up quickly, tell you a little bit about what we're working on this week, because there's a UAI deadline on Friday. Is to do a distributed inference. Remember I said there's this industrial revolution in data. Not only is there going to be a lot of data and it's going to be spread around on networks, but it's going to be noisy and wrong a lot of the time. We see this in sensor nets a lot. Sensors generate data with noise. A lot of these systems, if the raw data isn't noisy, what you want to do with it is noisy. So think about network logs. All right? If you're building like an intrusion detection system, your network packet log may be clean, but your log of intrusion decisions is noisy because it's some sort of soft process that you wrote up. All right? So either the data is at such a low level that you need to do noisy things on top of it, or the data itself is noisy, but data spread around in the network at this volume is not going to be like perfect. So the challenge is in real time, get interesting, valuable information despite uncertainty in the data. All right, and despite the cost of acquiring the data, you might not even be able to get all the data, so you'll certainly have uncertainty in that context. Okay, so there's lots of applications for this: building control, internet security, disaster response, robotics. And then for my database friends, I'd submit that any distributed query really needs to think. And you guys, I know Jin and stuff is working in this context, so you guys believe this here at Duke, that distributed querying should be dealing with uncertainty. Just should. All right, so the cool thing is that the algorithms for managing uncertainty from graphical models are graph algorithms, all right, that do transitive closure message passing on graphs, which is, 20 slides ago in this talk, we did it for networks. Why can't we do it for these graphs that these AI algorithms are using? And the answer is we can. The nodes in these graphs, for those of you who haven't seen it, they're random variables. The edges are correlations between the random variables. And some of the nodes are labeled as being measured, all right, that have data. And then the idea is you want to find the probabilities of the unmeasured nodes. And the way that's done is what's called belief propagation, which they describe in the AI literature as a message passing algorithm. They don't have a network in a computer sense, okay? They just have these variables, and the metaphor is messages are passed between the variables. These are probability distributions that are passed between the variables, okay? And so the game with distributed inference then is to take a physical network, build on top of it some kind of overlay network well customized to this task, upon which you layer this inference network. So the logical messages are passing on the inference network between these random variables. Map those down to perhaps relocatable addresses in an overlay network, which are in turn mapped down to physical addresses. All right, so somewhere down here, there's computers that can measure stuff. There's also computers that can compute stuff. All right, and you're going to map up from here through there. And each of these layers is easy to say in our language. And what's pretty fun is once you've said both of these layers in our language, you could consider co-optimizing these two layers to get an algorithm that's network efficient for good approximate inference. Okay, so you can trade off the quality of the answers against the efficiency of the networking layer and have control over both in a single language with a single optimizer. So step one of this is to show how easy this is to do, which is what's due Friday. All right, we've got 5 or 6 different variants of belief propagation, including very fancy ones, junction tree, exact inference, and some funkier approximate ones, variations of loopy belief propagation. So the fancy one is 22 rules. That's 10x smaller than the Lisp prototype, that the graduate student wrote. We found a bug in his prototype. And then we've got all these approximations that were easy to tweak out. And this is due Friday, so hear more. There's lots of fun research issues at each of the layers and then in the collapsing of the layers. So this is an agenda I'm pursuing with Carlos Gestrin and company at Carnegie Mellon. And it's quite a lot of fun. Okay, the other, boy, I really have to rush. The other interesting thing I want to mention is our meta compiler. So real briefly, we said that declarative languages are great, but we implemented P2 in C++. So something is wrong with us, right? We're not eating our own dog food. So we said, well, we got to put our system in the mirror and really believe in what we're doing. So we put this notion of declarative languages in the mirror, and when you put declarative in the mirror, you get something that kind of looks like Avita raced. So that's the name of our meta compiler. The idea is we're going to represent queries, that is to say our overlog programs, as data. We're going to represent our optimizations as queries. All right? We're going to represent the scheduling of various phases of the optimizer as a lattice, which is data. All right? And then this whole thing is going to get compiled down to data flow. All right? So our compiler is implemented in the language itself. And so all you need at the bottom is a little bootstrapping, the basic hardwired data flow at the bottom to get started. All right? Why? Because it's a perfect fit to this whole business, just like it is to everything else. So I'll spare you that. This is a query. This is the schema for a query as an entity relationship diagram. So we've taken our queries, we've turned them into a database. So you take the query, you shred it up, little properties of the query get stuck in little tables. All right? And then you run queries on the tables to do the optimizations. So dynamic programming is a small program in this language. Magic sets rewriting is a bigger program in this language, and so on. All right? So yeah, dynamic programming is 38 rules, magic sets is 68 rules, and happens to be a close translation of Ullman's course notes. I have to skip this cool thing about how eddies are related to the runtime for this, which is pretty neat. And that's all I'll say about that. So finally, I want to close. I'm out of time. And try to, for those of you who didn't get excited up to now, try to get one last gasp. So this is one of my takeaways from this talk. All right, this is not a talk about databases and networking. Okay, so what is this a talk about? Well, the big picture is the following, that this is really a talk about sort of three different things maybe. One is automatic programming. So there's this vision Jim Gray had in his Turing lecture that Butler Lampson echoed in his 50th anniversary of JACM article, that we really need to solve the problem of automatically programming computers. The idea that we're programming them line by hand imperatively is not going to scale. All right? And this was set out as this really hard thing to do, and Lampson said, works great for spreadsheets and SQL, doesn't seem to work for anything else. So I'm trying to chip away at that one domain at a time. And that's kind of one of the things about this agenda is how far can we push automatic programming, high-level languages? And I think that's a very important agenda for computing. Another one is parallel data flow runtimes. So what are we doing at the runtime? We're doing data flow. Data flow is a very old idea in computing, and it's come back into popularity with MapReduce. Okay, and it's come into the fore again also when thinking about many core and how we're going to deal with many cores. Right now, the tendency seems to be to think that data flow programming is great for these dorky MapReduce programs that are one pass, vomit the data through the system, but not good for anything else. And on the flip side, there are these really hard scientific computations in some Turing complete language like Fortran. And what we're trying to do is identify places in the middle. Okay, these protocols that we showed you are not embarrassingly parallel in the sense that most MapReduce programs are. They're also not, our language is not Turing complete on the flip side unless you start calling functions and stuff. So what is that sweet spot in the middle? Let's find it and let's exploit it, let's parallelize the heck out of it automatically and keep the programming metaphor really high level. All right, and then the last piece, which is also very exciting, I think, is the idea of getting the machine learning community, which doesn't tend to be systems heavy, all right, and doesn't tend to be interested in doing a lot of program whacking. Let's get them into the network because we really need them in distributed systems. And if we can give them the right programming languages, they will come. And I'd rather have those people doing machine learning with my language than have me doing machine learning. All right. So, all right, that's it. At this point, I guess we'll take questions from the air. Anybody out there in the hinterlands? Okay. How does it compare to? I'm sorry, I can't ask what you're asking me to compare. He can't hear what I'm to be comparing it to?
ML.
ML. ML is a functional language. It's Turing complete. This is a logic language, and depending on how many bells and whistles you throw in, it's not. I think both are fine starting points for this kind of endeavor. As I mentioned, I think the notions, at least for networking, of rendezvous of sets of data or streams of data and graph computations are very natural in this context. And those are not sort of as natural in ML as they are in these logic languages, which are sort of set-oriented. So, but I have spent time reading Haskell manuals late at night trying to figure out whether I should learn more about functional languages, and I think I probably should. I don't know if that answered your question.
Oh, thank you.
Sure.
Yeah.
Yes.
Yeah, you folks in the database community think about execution plans every day, right? For somebody who's sort of more used to thinking about these kinds of problems in terms of the sort of procedural approach and the protocol-centric approach, there's still, for me, it's a little bit fuzzy, vague to me how you actually get from the declarative specification to an execution of the program that you want. And some of the stuff is very reminiscent of, Prolog, right, where you have a declarative specification, in a logic language of what you want, but at the end of the day, you end up sort of sticking a lot of hacks into that in order to be able to control the control flow, right? The underlying backtracking to run your program. And I wonder if that same kind of gap exists. At some level, this is magic, right? You declare what the specification of what you want, and it just works. But
it actually is magic. Yeah.
So I guess really what I'm asking is, is there an interesting set of issues there that's being swept under the rug?
Yeah.
So
I will echo something you said, and then which will be slightly facetious, and then I will answer your question. So as a true database guy, I have to say that Prolog is a horrible, horrible thing. And the reason it's a horrible, horrible thing is exactly what you said, is that it takes what was supposed to be a declarative language, and then it says, oh, but you need all this imperative stuff in it. And you need to understand how the runtime works, because without understanding the runtime, you can't understand all these hints you're giving the runtime. And so now there's 7 people who can write these amazing Prolog programs, right? But you have to grok the runtime as well as the language, and it's really not at all declarative. And so all the data log guys in the 80s would jump up and down about this, okay? And I'm just echoing what I was taught in graduate school, right? I was brainwashed. I'm trying very, very hard to not do that in our language, and yet there are cases where we're doing some of it. And so I'm trying to iron those out. I think some of them can be ironed away, and I'm working with PL people now to get that right. But let me give you an example of some of the things we're struggling with, okay, which maybe aren't so easy to iron out. They have to do with state, and they have to do with state and time. So one of the things I didn't get to in this talk, which you may have heard from Boone last year, is this is not just a database, because the data doesn't persist forever. It's soft state typically, or even zero lifetime state. It's event streams. All right, the events disappear just as soon as they're matched with stuff. All right, we have a model for that in terms of soft state relations and what that means. That kind of works, okay, but it's a little complicated. You have to reason about it. The programmer has to reason about it. So we have a statement about the lifetime of records and tables, and you have to think about that. So that's one issue I've sort of swept under the rug here. A second issue is that because we have these streams and they affect these derived tables, but then their inputs disappear. Right, so you can imagine a packet comes, it triggers some behavior because it joins with something, okay? And then the packet, because it's got zero lifetime, it's from a zero lifetime table, it evaporates. But its effects are supposed to affect some table. So you're making state transitions. And when you start making state transitions, you could imagine there's some question about, well, what order do you make them in? And things get a little funky. So I'll give you an example. So we wanted to implement the Symphony distributed hash table. Symphony it's a small world graph kind of model. So you're trying to build a random network. And the way it works is people send messages to random people in the network saying, can I be your neighbor? And if you're receiving some of these messages, you're supposed to say yes until you hit some threshold, like 10, after which you're supposed to say no. All right, so the order that the messages arrive determines which 10 will be the winners. Okay, so that's already got some timing issues. And then the second thing is the rules that say, when you receive a message, check to see if you've already got 10. When you receive a message and there's fewer than 10 things in the table, insert into the table. When you receive a message and there's fewer than 10 things in the table, send an acknowledgement. Those are 2 independent rules. If 2 messages come in and they handle those rules in different orders, you get a race condition, you get 11 things in the table. That's not so good. So suddenly we want transactions. And you're sort of like, wow, declarative languages and transactions, they seem to go together. It's like, 2 great tastes that taste great together. But we'd like to not have to do that because it's more things to reason about. I think some of that can be taken care of with the appropriate temporal semantics in the logic. So some of the things about ordering, for example, you might have a semantics that say any 10 is the interpretation of this program, not which 10. And those semantics could be well-defined in the language. The programmer has to reason about them. Right now, it's not even well-defined. You got to understand the runtime. The atomicity thing, I'm not sure about. So we're struggling with that a little bit, whether that can be made to have a high-level interpretation that's implementation-free. So we'll see. So very insightful question. I hope that was at least a hint into some of the problems. I still don't think it's as bad as cuts in Prolog.
I'll take your word for it.
Okay. Well, we can't end on the dirty laundry question. That's not fair. Yeah.
Has anybody tried applying this to cache coherence protocols?
Wow. Has anybody tried applying this to cache coherence protocols? No. So Paxos and things are sort of kind of smell like that a little bit. They're replica consistency protocols. The guys at Texas are doing replication for distributed systems protocols. So it shouldn't be that far a leap. I wouldn't want to have to run this at the speeds you need for cache coherency protocols. I mean, that's just not something I've been thinking about taking on. But that said, we are thinking about, as a future target, now that we have this Evita erased thing, we can pull out our compiler from our P2 backend, and we've retargeted it at DSN. So we have one compiler for both DSN and P2 right now. We're going to do it for MapReduce. So my student's going to spend the summer at Yahoo doing it for Pig. So we'll be compiling our programs into big parallel data flows. We're thinking about doing it for multi-core programs. So data flow multi-core programs, which actually don't need to have cache coherency because the data is all partitioned. But once we get into that performance domain, if we really go there, maybe it's worth looking at. So that's an interesting thought.
I mean, would you have a Verilog backend, for example?
You know, it's not that outrageous. We looked at the John Warzenik at Berkeley has this thing called RAMP, which is a FPGA emulator for architectures, and they have a sort of data flowy looking runtime that a graduate student for a class project was supposed to compile us down to, but never finished his homework. Yeah.
So I have a question about your initial vision that most of the data is going to be automatically generated. So what's your feeling in terms of the fraction of that that's actually useful data?
Well, you got to define useful. I'm not even quite sure how to answer that. I mean, many computations can be answered on samples. Much data in databases is arguably not that useful until it's the query that wants that data, so to speak. So, right. So if you're doing aggregate statistics most of the time, you don't care. And then maybe somebody wants to trace the source of a packet. You know, why did I get this packet? And it goes down and looks at the individuals. So it's hard to know what's useful. All right. I mean, and you could ask Google the same question: what fraction of web pages are useful? And they'll sort of tell you, well, this stuff is spam, but still it affects the statistics they use to drive various decisions they learn from the spam. That's a very philosophical question. So I'm just not going to answer.
Okay. Fair enough.
Okay. Yeah.
I think it might actually be the same question again, but so that the Practi replication, the University of Texas stuff, or some of these other sort of declarative flavored languages for distributed systems like MACE, they seem to be based on, they have much more of this flavor of some set of canned building blocks, you know, design patterns, even click, right? You've got these various sorts of off-the-shelf kinds of stages that you can string together to make programs, and there seems to be much more of a flavor of that in some of these other systems. Mm-hmm. Do you see that as are you actually going? Is my perception correct that you're going in a different direction here, by taking really a much more sort of data-centric, data transformation kind of approach?
Yeah, that's an interesting question. Philosophically, maybe it's the same thing at a different granularity or something, because we do envision, and we are seeing, taking piles of these rules, packaging them up, having a way to define a clean interface instead of, here's my pile of rules you can include in your program, which is our current interface. But if we had a nicer encapsulation mechanism, which we're adding over the next year, I think, we are expecting there will be off-the-shelf things like Paxos, or content-based routing, your favorite DHT, whatever it is, maybe you don't care. And that people will put those building blocks together. Those are much bigger building blocks. Now, another thing Lamson said in that 50th anniversary JACM article is that in talking about automatic programming, he talks about reusability of code and how this was a big vision in computing that arguably failed when you look at all the VB modules in the world that do the same thing. But they succeed in big pieces. Like people reuse the notion of database, and they reuse the notion of web server, and they compose those. So, not to say that Lamson is backing up what I'm saying here, but it seems modularity at a high level people can think about maybe more constructively the modularity at the level of there's a click element for, I don't know, some small congestion control element, something like that.
Joe, you have, I think, so when you showed that one slide, I guess you have operators in which you're taking language and mapping it to operators, the data flow, right? Maybe that could be treated as a library, and you could expose that interface.
Yeah. So we could
Would it be fair to
expose
say?
we could expose not overlog programs. We could expose data flow segments as well that you could program with in a data flow way.
Right, would that be the approach that Mace is taking, like coming up with a library and then you could string up these operators?
Maybe. I mean, Mace doesn't, correct me if I'm wrong, but my understanding is that Mace, we have a fundamental abstraction of data flow, and I don't think Mace does. And so it's a distinction right there, sort of a programming model distinction. They're much more like a von Neumann machine, and we're like a data flow machine. And so
Right.
it's just a different starting point. But you're right that we could advertise a finer granularity interface if we chose to.
Mm-hmm.
Yeah. Yeah, that's true.
So how do you debug a data flow?
Oh, great. So the question was how to debug a data flow. So first I want to share a reflection from a Stanford graduate student who works for Monica Lamb. So that's a compiler group, and they had a project, John Whaley did his thesis on this, where they were using Datalog a Datalog engine to analyze call graphs in programs. All right, so very much the same insight we had, kind of contemporary with our first paper, that you have all these call graphs, you want to run analyses on them, let's implement a Datalog interpreter for that. And I asked them, what do you guys feel about programming in this language, and what kind of bugs do you get? And they said, first of all, there's a ramp-up time, but it's not that long. In a week or so, our students usually can make progress. And second of all, the bugs we get are not the kinds of bugs we get in traditional languages. We get sort of these logic bugs. We get bugs in the specification, and so the reasoning about what's broken is not quite as case-based sort of as you do with debugging C code or something like that. It's sort of you were thinking wrong kind of bugs, and you got to sort through those, so that's tricky. Now, a more pragmatic answer to your question is to describe this Eurosys paper that Petros Maniatis did on how he implemented debugging features in P2. And what they basically do is you can tap points in the data flow and expose them as relations. And then you can look at those relations, but you can also specify constraints on those relations that will stop execution globally. And the way that's done is by doing this Chandy-Lamport snapshot. So they actually are taking consistent snapshots of the global system, which is pretty slow, okay? It adds a lot of communication. And then you can stop the system at some consistent state that violates an invariant or matches a test. Okay. So, and they were also, by tapping these data flows, they're able to attribute through a sort of data provenance reasoning why a packet arrived where it did. They can tell you which rules and which data items at the fronts of those rules generated this packet. So there's a packet tracing aspect to it, which is sort of nice. It's a very high level debugging. You're asking, well, why did this message arrive? It's a pretty nice question to ask, actually, as opposed to, how did I get to this line of code? Yeah.
Only kind of going back to Jeff's question.
That's totally fair.
You had that example with the links and paths, and then you put the @ sign in to specify where the data should be. And then you showed that, well, what you could do is you could have links, which is if it's a source destination link, it's a table that's laid out at the sources, but copied over to the destinations, and then the path, I'm not sure what you call it, clause, is in the same place as the link clause, so you do the rule of inference there. But, and presumably this idea of duplicating the link table wasn't in your rules. That was something the compiler figured out to do. The compiler could have said, oh, well, let's move the path
Exactly.
instead.
And that's
then
how
I
you
can
get
imagine there could be a
dynamic source
disaster
routing.
if you move the wrong thing.
The disaster is a performance disaster, to be clear. Okay, so the
But
program
performance
the
disaster.
program retains its semantics. The rules are sound.
Right.
All right, and the rewrite you described gives you dynamic source routing. So it actually
Oh, this is the example you were saying, where depending on which way it went, you get one protocol.
you get one protocol or the other. And is dynamic source routing a disaster from performance in some environments? Yeah, because you end up using up a lot more bandwidth than you need to because you're doing source routing when you didn't need to. Okay,
Right. So
Right,
is
so
that
there's
the
a
kind of
performance-
place where
hit for that.
right? So that would say, let's put in like a vertical slash that says this one is the one you should move, and we'll call it a cut. And
No. This is where the database people jump up and down. They say, no. What you do is you estimate the performance parameters of the network, and the optimizer makes that decision. So in this case, it would be packet drop rate or something like that. Would be what determines whether it's worth doing source routing in a patch of the network. All right. So it's churn measurements would be the statistic of merit, and then the system under the covers should be monitoring that. Oh, and by the way, what's a good way to monitor properties of your network is to write queries. Right, so I want to write a query that finds for each little patch of the network what the loss rate is, or for each link what the loss rate is. And I can easily add such queries to my metacompiler. All right. So no, that's religion. You just defended my religion. Well done.
while I'm offending your religion, so
Yes.
some people, some wags in the community, noting that this kind of builds on Berkeley's network of workstations project,
Okay.
would want it to be called Now What instead of
Ah, very nice. Very nice. Yeah. Good. The cluster version should be now what? That's excellent. Thank you. I will
Tell Dave
attribute.
Color that.
I'll tell Dave color that. Okay. I'll attribute it to you when it comes up. That's good. All right. Thank you.